I'm Won-Lee. Today's topic is transformation. Today, explanatory variable x, transformation of x. Next time, transformation of y. Okay, let's see what y we need to transform variable. Here, a simple linear regression model assumes a linear relationship, so linear, between y and x, and that the assumptions about the error terms are satisfied. Model includes assumption about error epsilon. However, if these assumptions are not met, the model cannot be treated as a linear regression model. Therefore, if the relationship between y and x is not linear, or if the assumptions regarding the error terms are not satisfied, it would be appropriate to transform variables and conduct regression analysis. The main goal of regression analysis is to find a more precise, accurate expression of the relationship between y and x, while it must be addressed within the range where the assumptions are satisfied. This is important, okay? Assumptions are satisfied. If not satisfied, you cannot use the result of regression analysis. First, transformation of x. Transforming the explanatory variable is necessary when the assumption about the error terms are not problematic. But the relationship between y and x is not non-linear. Okay? It can be identified by obtaining a scatter plot of x and y or residual plot. So you must check the scatter plot of x and y or residual plot. Let's see. First, there are three simple transformations: log x or square root x. This applies when the relationship between y and x resembles the logarithmic or square root function, like this, okay? As shown in graph A. X and y relationship like this, from you get the shape obtaining a scatter plot of x and y. And x squared or exponential x. This applies when the relationship between y and x is quadratic or exponential, as shown graph B, like this. This is what, quadratic or exponential. But the thing is, the range of the distribution is constant, okay, in a certain band. The data are scattered in a certain band, like this. 1 over x, or exponential power minus x. This applies in the cases where the relationship is reciprocal or involves an inverse exponential function, like this, okay? 1 over x or inverse minus x power in graph C, like this, okay? This one, the dot line is the data, okay, are distributed consistently like this in a band, in some band. Then you may transform x, explanatory variable x. It is a little, okay, simple thing. Let's see example. The following data pertains to the training period x, a day, unit is day, and performance y of new sales representatives, salesmen, okay, training period x, and y is amount of sales, 0.5, 46, 0.5, 51. They are, what, 10 persons. As a result of processing this data with a linear regression model is y hat equal to 34.35 plus 36.9x. R square is 0.97. It is a pretty high R square. And p-value is 0.0, almost 0. The residual plot obtained as follows, like this. Residual plot is what? This one is a studentized residual. Here is y hat, okay? Studentized residual. So you may see there is some pattern here, like this. What is this? This is quadratic uh, parabolic shape. Although the residuals are distributed within a constant band, okay, they exhibit parabolic shape like this, has a somewhat pattern. So we will only transform the explanatory variable x because it has a consistent band. In other words, when we take the square root of x and perform regression analysis, the result will be y hat equal minus 11.69 plus 85.56 square root x. Okay, r square will be 0.987. Comparing this r square, a little big r square we obtained, and the p-value 0.026 for intercept and 0.000, almost 0, for what coefficient of square root x. And the residual plot from this result is follows like this. Residual plot. This one is residual plot. Okay. This does not indicate some pattern, random pattern. It shows random pattern. So we will be satisfied with this kind of a residual plot. So you better use this result. Okay? Even though the problem is resolved through variable transformation, the biggest challenge of nonlinear regression is that interpretation is not straightforward. Interpretation problem. In other words, in the case of a linear regression, an increase of 1 unit in x means the specific increase in y. You may explain the coefficient, right? 1 unit increase of x implies 36.9 increase of y. However, interpreting an increase of 1 unit in square root x, what is this? 1 unit in square root x is more difficult. In nonlinear regression, it allows for more refined regression line. This is better, what? Better refined regression result, which means a prediction can be made with greater accuracy. Prediction is good. This non-linear result is for prediction, better prediction than this linear result. But anyway, interpretation is not straightforward. You cannot explain the result to other person. The relationship is better, but interpretation has some difficulties. Okay, thank you. Bye.